Okay, so like I said, we're going through these. I will miss tomorrow. What I'll probably do is go home and make a video. You may hear my 5-year-old running around being a brat during the video of what tomorrow's lesson should be. We're going to be in illegal rows. I don't know why this has to be on YouTube. And stay that way tomorrow. So if you want to bring your earbuds and listen to my melodious voice talk about 3-1 day 2, fine. A lot of that I'm going to do today is probably going to be sufficient, though. So we're nicely taking 3-1 in 2 days. What's the next one? What's the square root of 4? Answer the question. 2 to the 5th. Bam. Like ninjas. All right, and then you can never leave an answer with negative exponents is usually the rule. So sure, this is 2 to the negative 12th. What does that become? Don't give me a number. It's 1 over 2 to the 12th, meaning don't try to evaluate that without a calculator. That's a very, very, very small number, 1 over 2 to the 12th. What's a to the negative 6th become? 1 over a to the 6th. And this is all redonkulous. You get it all. There's that color scheme thing. But then a negative times a negative is a positive, so you get b to the 15th on that last one. And then these are just silly calculator questions. So you would have just gone ahead and plugged those in. Notice what I note to self, though. Not that you care about this, but I think like a TI-89, which people don't buy anymore, didn't even have a square root button. Because you can take a square root, and instead of square rooting a number, you can raise it to the what power? 1/2. So this 5th root, you can actually evaluate this by raising it to the 1/5 power. Now some notes to self. What's x to the 3rd over x to the 3rd? What is the answer to that? 1. We know that because we have something divided by itself. But there's the subtraction rule that creates 2 other rules. Okay, so what am I supposed to do with the 3's? Like when we were told what we do with exponents, maybe by our Algebra 1 teacher. What are you supposed to do with the 3's? X to the 3rd over x to the 3rd. What's 3 minus 3? That doesn't mean you get 0 for an answer. It means, I just lost that 3. Let's go back. Okay, that means you get x to the 0, which beget the rule, what? Anything to the 0 power is what? 1. This is the reason. If you use the subtraction rule, then you get x to the 0. Well, that's because x to the 0 equals 1 because it came from x to the 3rd over x to the 3rd. And then also, what does this give you? A to the 3rd over a to the 9th. Stop! Where are there more a's? On the bottom. How many more? So it's 1 over a to the 6th, which is what this student was about to sprout out. I cut him off. But then what do people do? They take 3 minus 9 and get what? A to the negative 6. So what's going on here? These are equal. So the negative exponent rule comes from, the subtraction rule yet again. All right? All right. Here's your illegal notes for the day because it's chock full of information here. This is supposed to be review. Many of it will be. But you might want to make a note to self and create note to self and make a little skeleton. What are the pieces that I should remember? And some of them you should hopefully need nothing. All right? But like number 3, that's going to be a little unique and different. 2, we just did in the bell work. Be honest with you. If you know what happened in the bell work, you know how to do 2. And 1, you have a new game at lunch. Not polynomial, not a polynomial. Exponential, not an exponential. Well, this should be a game board. There should be it's like Trivial Pursuit. You have little pies for different kind of games. Okay, so the first silly little game is exponential, not an exponential. All right? So, I just cut out what the book said. The first one in yellow, which is then, it's frozen. It's just screwed up all day. All right, the first one in yellow is thrown out here in blue over here. You know x squared is a monomial. It's just a term. That is not exponential. That comes from the polynomial family that we just had a chapter on in chapter 2. An exponential is when you have a variable in the exponents. That's an exponential. Okay? So that's one thing. Your game today to start off your homework is exponential, not an exponential. All right? Then I'm just going to shove some answers when we actually play that. Then I think it goes to 3. If you looked at that core that I gave you, when you hear or see the definition, you see the directions, that's the D word I was looking for, and it says the data models an exponential function, stop. Okay? To mirror that data, this is the formula that you're going to use. Y equals A times B raised to the X. That's number 3 on what we're going to do today. We actually have a couple different ways of approaching that. And actually, you're going to have that tomorrow as well. You're going to think tomorrow's word problems are super big numbers and super scary, and they're as easy as the ones we're doing today. All right? They really are. All right, but so when you see that, you need to pull this out, and then what you need to do is find A and B. By the way, A is called the initial value. You want to know why? Well, I'll tell you. The initial value comes from, like, let's think of time. What's the beginning value? The beginning value is at time what? 0. What happens when you plug in 0 for x? What's b to the 0, everybody? 1. 1 times a. A is the starting value. Very simple to understand how A is the initial value, because most cases start at time 0. A lot of our things that we're going to do in real world questions are, population over time. At time 0, that's the start. And so on and so on and so forth. B represents the rate of increase or decrease, and you'll see that when we actually get through the rest of this week. All right, so first game. Polynomial, wrong! Exponential, not an exponential. I got screwed up with my games. You can see the first one is exponential. Why? There's a variable in the exponent. Then if you read all of this stuff, it says, for those that are exponential, state the initial value. Notice what I snuck in green in front of that 3. What number did I sneak in front of there? Or, what's 3 to the 0? The initial value comes from plugging in 0 for x, the starting point. So, the initial value is 1, as you can see, and the base is 3. 4 is not an exponential, even though there's an exponent, because what's 4 squared, everybody? There's not even a variable. That is a horizontal line. So it's actually called a constant function, even though it does create a line. Then the third one is from our, that's not even a polynomial, that's our power function section. Okay, so again, it's a silly start in the homework. Whoopsie daisy. Okay, next one was part 2 of what I said, our little skeleton of what we're going to be doing today. Evaluating, which I said was the bell work. I don't think we have to spend a lot of time on this. What's 2 to the negative third? If you say negative 8, get out where? The weeds. What's 2 to the negative 8, everybody? 1 over 3. So I'm not giving you a chance probably to write these notes down, but I'm not sure we really need them. I'll pause after the video, or I'll pause the video and let you take these down. So what's 2 to the third? 1 over 8, and then what's 1 over 8 times 4? So that's easy. Not as so much maybe, but something like this did happen in the bell work. Now this is what drives me nuts. Sure, 2 to the negative third is not negative 8, but then some crazy stuff occurs when we have a negative fractional exponent. So negative exponent, we do what with the number? Flip it, don't we? But then why I say that is, what a lot of people do sometimes? They flip the negative 3/2 to become positive 2/3. They make up their own math. All right? That's not what occurs, everybody. This is what occurs. Really, it becomes 3 times, holy crap, 1 over 3/2. 1 over 9 to the 3/2, I mean. So it's 1 over 9 to the 3/2. This is how you employ the negative exponent rule, just like the previous question. Look at them both, if you're cloudy on this one. And then what's 9 to the 3/2? What do you get? How do you get 27, those that whispered that? The square root of 9 is what? 3 to the third is what? And then that becomes 1/9. Okay, third thing you're going to do, and again, the reason I gave you that little course so that your mind doesn't get jumbled. So even though I said Chapter 3 gets a little bit better, they take exponents and try to approach it in 5 different ways and have you do 5 different things with them. Okay, so do pay attention to this because I gave you number 11 for homework. So I did number 12. But you have to understand for number 12 and 11, they're accessing the same table. But the x's are for both these functions, -2, -1, 0, 1, 2. Then for number 12, they want you to find g of x, very easy for me to say, which is these created y values from these x's. You have to do number 11, which is going to take this chart and put them together and come up with an equation. So again, number 3 in your core of what you have to do today, when you read the word exponential, this is an exponential scenario, your brain file must be this pulled out. Boom! Whenever data fits an exponential model, this is the model that it mirrors. So my friends, if I can call you that, what is the initial value? What is the initial value of this scenario? It's hiding in the table. Actually, it's not hiding. It's taunting you. It's not 3/2. It's 12. Why? Actually, it's how you can start this little shindig off. You can plug in that 0, 12 coordinate. What's b to the 0, everybody? What's b to the 0? 1. So 1 times a equals 12. A must equal 12. So I just said, what's an initial value in a exponential situation? The 0, value. And it happens to be 12 on this one. Now, I don't care how hard this gets. This one's actually easy. I actually literally could take any of these other coordinates and plug them into my new function, replacing a for 12. But the smartest one is to plug in this one. Why? Because what goes in for x now? 1. And then what goes in for y? 4. Now, again, tomorrow, your initial value will be 0, your second maybe 10, and all I have to ask you is, how do you solve for b to the 10th? What do you have to do to both sides to solve for b to the 10th? How do you get b to the 10th to be b? 10th root it, which is a calculator question. So it's not hard what you're going to hit tomorrow with these crazy values that you might run into. So the answer is that, and I'll open the floor for any questions, which nothing's happened so far. It wasn't on video. That would have been fun. All right, here we go. Okay, don't get all... I gave you 13. Here's 14. Doing half your homework. Well, it's not really, but... First of all, what's the key word in the directions? I'll give you a hint that's circled and underlined. It's exponential, so the brain file, a times b raised to the x. This is exactly the same as the other question, except I'm only given 2 coordinates, not like 6 or 7 or 8 data value coordinates. Okay, so you're lucky. It actually doesn't always have to be 0, given. As a fatter max, it could be 2, and 7, You know what you'd simply do? Set up a system. You'd set up a system and solve it by substitution. I think that's what's going to happen to you tomorrow. All right, but this one, what's the initial value? What's the initial value? 2. And then those that don't get it, this is y. I plug in 0 for x, and I plug in a, but I plug in 2 for y, and then a becomes 2. So a equals 2, and then you reinsert that in, and then you plug in the next coordinate, which is 2 over e equals 2, the newfound, and then luckily 1 for b, which is real simple. Now, just to speed this up, multiply both sides by 1/2 as opposed to divide by 2, so you can see what happens with the 2's. What actually happens? Oh, I thought maybe you were sleeping. All right, b equals 1 over e. So what's the final answer? Y equals 2, the initial value, times 1 over e. 1 over e, right? I didn't go too fast. Raised to the x. You did this last year. We're going to do a real quick analysis on these two functions. It's not really a big deal. I picked 3 to the x and 1/3 to the x. What's 3 to the 0 power, everybody? Do you hear them on YouTube? There's only 1.5 students in here. That's what it sounds like. What's 3 to the first power, everybody? 1 comma, 2 comma. It's already getting redonkulous. Negative 1 comma. What happens when you plug in negative 1 for x for this first one? You get 1/3. So I should be putting these here, but I'm getting tired. What's negative 2 comma? 1/9. So what happens as you plug in negatives, large negatives? What is the numbers? What do the numbers for y become? Almost what? We get annoyed. When we get annoyed, we draw a what? Because it's very impossible to keep getting closer and closer to the x-axis without touching it. So we put a border there to tell you and me, tell yourself and everyone else that's looking at your picture, that the graph is getting close to 0 but not quite getting there. All right, what happens when I plug in 0 into this one? What do I get? No time. What happens when I plug in 1, though? 1/3, 1 student. What happens when I plug in 2? 1/9. What happens when I plug in negative 1, though? We get the old flipperoo, and now it turns into 3 and 9. So actually, when we go this way, the graph looks like this. I missed that point. We'll fix that. There we go. Now, what's this graph on the left doing? Increasing or decreasing? Increasing. What's this graph doing on the right? Decreasing. Let's fill out these limits. And by the way, does it really matter if I put 5 to the x, 10 to the x? Yes, it does. But would the shape be any different? Just be a little bit steeper, right? So the idea is when b is greater than 1, this is the kind of picture you're getting. When b is between 0 and 1, you're getting this decreasing scenario. Okay, so I know I'm fast tracking this because we did this last year. What's the limit of y as x goes to infinity for this picture? As x goes to infinity, where does y go? Infinity. But as x goes to negative infinity, where does y go? 0. And then it's flip-flopped. As x goes to infinity, y goes to 0. As x goes to negative infinity, y goes to infinity. Okay? So, I'll hold off for a second. Any questions? Okay, now, are you going to take all this down? I hope not. Refer to figure 3.3 in the book. And actually, do you know what this looks like? This looks like your function book. Remember the 12 functions? It's okay, student number. I wish we had numbers. Group 1, 3. He almost fainted. All right? So remember that from your book? There's a horizontal asymptote for both these pictures. And then this is what I said. You know, if b is greater than 1, 2 to the x, 3 to the x, 4 to the x, 5 to the x, and so on and so on and so forth. You have the picture on the left. 1/2 to the x, 1/3 raised to the x, 1/4 raised to the x. You have the picture on the right. And read all the other stuff. It's great reading. But of course, we could take all of these graphs and shift them, reflect them, dilate them. We actually can vertically stretch and shrink them, but we also can horizontally stretch and shrink them. And I don't even want to put it all together with this one. And I hope you can see my highlighted green. Okay, see that? Not highlighted, but that super bright green? Because that's real subtle. That's a y-axis reflection. What we're saying is I could have b raised to the x, and I could do all of these things that I color-coded here. I don't know if the color coding quite works. All right, but you can denote maybe by me drawing some lines. The negative out in front is actually an x-axis reflection. But a negative on the inside of the exponent is a y-axis reflection. And all the rest have letters that denote stuff. Now I know I said an exponential is y equals a times b to the x. This a is actually called the vertical stretch shrink factor. All right? So you don't have to get overblown by, how does that compare to concept number 3 that we did? You can relate them, and it's still fine. Might want to write down. What I did say right before I stopped the video was the y-axis horizontal stretch and shrink. Take a look what I write here. Okay, let's just analyze that by itself, because it's hard to put together with all this other junk. So y equals b raised to the x over, I don't know what letter you want to pick. Z is what second hour picked. You remember this? When you have a horizontal stretch and shrink, it's x over the number. And then when z was greater than 0 in this little spot, what is it? A horizontal stretch or shrink? Now z is bigger. I'm not 0. I meant 1. My bad, dogs. Okay, z is greater than 1. Is that a stretch or a shrink, do you think? That's a stretch. That's why they put this in this format. So a number bigger than 1 represents a stretch. And we're going to analyze this separately from all the other ones. And you'll see. But then when z is less than 1 in this position, that's a horizontal shrink. And I ran out of room to write horizontal. So put horizontal stretch and shrink separate, because this book is obsessed with horizontal stretches and shrinks. Most of the graphs that they put in there for you to analyze, a lot of them have horizontal stretches and shrinks, and I'm going to analyze that with you. Okay? Now this is the Mickey Mouse question that you dealt with last year. Very simple, very basic. Okay? You did all 4 pages, right? Front and back? Okay, it seemed fast. All right, just want to make sure. Okay, first things first, describe how to transform the graph of f into g. Now, one thing I will say about this book, and you'll see this later, is their exponential notation's not very good. This is all right in the book. I'll show you something later. Okay, that it doesn't really show up. But hopefully you understand everything's exponents right now. So that plus 4 is on the inside of the exponent. So which way does this go? Plus 4 on the inside. 4 to the left is correct. And you can actually have this happen. It's very simple. What do you start by plugging in? 0? No, because you get 3 to the 4th, which is 81. 0, 81. You plug in negative 4. What's negative 4 plus 4? 0. What's 3 to the 0 power?
1.
There's your starting point of where 0, 1 ended up. It got moved 4 to the left. Okay, so negative 4, 1 instead of 0, 1, the parent. And then 3 negative. Negative 3 plugged in gives you 1. 3 to the first is 3. Negative 2 gives you 9. So these are the ones that go here, and then the graph still does the same thing. The asymptote doesn't move, because I just got moved left 4. So may I proceed? I will. This is one of those tricksters. This is one that you should remember, because you remember all functions are affected the same way. So what should I do with 5 minus x? I should factor out a negative, and then what does 5 minus x become? So what should that become then? A move 5 which way? Ooh, let me write that second. 5 which way? 5 right. And then what does that negative on the inside of the exponent do? So y-axis reflection. Which one do you do first? The 5 right or the y-axis reflection? The rule is always blanks first. Always blanks first. Always blanks first. Reflections. Watch what happens when I move 5 right. 1, 2, 3, 4, 5. Then reflect. I'm over here for that point, right? Let's y-axis reflect. And then let's move 5 right. 2, 3, 4, 5. Isn't that a completely different spot? Isn't it? Isn't it? So if there's a difference, there's only one right way. You know how you figure it out? Hey, everybody, let's plug in 5 for x. What do we get? Okay, if I plug in 5 for x, what's 5 minus 5? 0. What's 0 times negative 1? What's 2 to the 0? Boom, shaka-lockers. Reflect first, then shift. Reflect first, boink, and then shift. 1, 2, 3, 4, 5. By the way, is the asymptote moved, yes or no? No. So when I plug in 4, what's 4 minus 5? What's 4 minus 5? Actually, it's easier here. What's 5 minus 4? What's 5 minus 4? What's 2 to the first? 2. I'm doing graphing 101 to check myself before you wreck yourself. I'm not graphing these. These are redonkulous. But if you're a non-note-taking person right now, we'll just go with person. You better look at this one. This is a monster. Remember what the directions say. They say, how does f of x turn into g of x? I'm not graphing it because there's too much going on here. We could go to the graphing calculator and try to see everything, but not everything is going to show up the way you think. That's the problem. So I just want you to identify. What does this 2 do? That is a vertical stretch. Wrong. Hold on. It is right. I need to do something, though. This is all cattywampus on the inside here. I got to do something with this. What do I got to take out so I can assess everything correctly? -3. Then we'll assess. What does the inside become then? X what? -1. Now, what's the 2? That's a vertical stretch. Okay, and then here's what stinks. I'm not changing colors because there's too many of them. What does that do? What does that negative only do? What is that? It's a y-axis reflection. Then, what does this 3 do? Hold the phone. Let's put this like this. Y equals e to the 3x. Let's just analyze that. Which is e to the x over, anyone? 1/3. So what does that 3 do? Does it stretch or shrink? Oh, it's a horizontal shrink by a factor of 1/3. That's the kick in the, let's say, stomach. Those are such a pain in the behind, but I think I know what they're trying to do. And actually, you know what I'm going to do in my graphing calculator? We're gonna put e to the x and e to the 3x and see the horizontal shrink. What does shrink mean? Am I going to go towards or away the y-axis? Horizontal shrink means towards or away the y-axis. Towards. Towards. So we'll see that when we actually analyze the picture. We got one more thing, though, before we actually do that on the graphing calculator. What's that -1 do? 1 right. That one's easy. You see how I mean that if you tried to analyze this, you wouldn't be able to get everything because there's too much going on. You wouldn't be able to see all of these changes, I would think. It's a little bit tough. Okay, we're going to go to the graphing calculator. Like I promised, we're going to go to the graphing calculator, look at y equals e to the x, and then look at y equals e caret 3x. And then I blew your mind when I said that's actually a horizontal shrink by 1/3. Watch this graph. It is what to the y-axis? It is what to the y-axis? Closer. That's what it means to shrink towards, shrink horizontally. You get closer to the y-axis. So there's my proof by a factor of 1/3. Okay, and then one more thing. What's this 3 do? This is 24. How does F turn into G? This is a vertical what? Vertical stretch. This is a what? Oh boy. Horizontal what? Shrink by a what factor? It's actually 1/2 the way they actually rewrite the thing. And then what's the -1? 1 down. And then remember, what do you do first? Okay, do you do the down one, horizontal shrink, vertical stretch? This is order of operations. You do this, this, and then that last. But watch out for reflections. Okay, reflections are very picky. I'm going to do all 3 of these graphs. These are more basic Algebra 2 questions. Let's look at number 1 real quick. What is number 1's change for the picture? 2 to the negative x power. What does that do? That is a what kind of reflection? Y-axis. And then what's that -2 do? 2 down. Who are we talking about? We're talking about compared to the parent. The parent is this one, and I'm just going to do it as a dotted picture. And it's those 3 points and then end behaviors that I want to care about on this. So what do? I reflect this over the y-axis, and then I go 1, 2 down. But who else goes 2 down? Who else goes 2 down? reflect it over the y-axis, but then go 2 down. Okay, so who else goes? Oh, I'm sorry. This is a horizontal. And then, so who moves 2 down? I feel like I did something wrong there. 1, 2. Okay, so reflect over the y-axis and then go 2 down. So where's our new asymptote at? That's what's crazy. Y equals 2 negative. Okay? And then this is what the picture does. The only one I didn't reflect was this one real quick. Reflects and then 2 down. So this is where the new picture is. Okay, so then what? Real quick, what's the domain of this picture? What's the domain of that picture? It's everything. But what's the range? That's a better question. What's the range? It's -2 to infinity. And then now this changed from increasing to now what? Decreasing. What's the limit as x approaches infinity? -2. But as x goes to negative infinity, okay, it's infinity actually. Okay? And then I don't have time to do these other ones. This is just an x-axis reflection, 3 right and 5 down. So last one, you got it, solving these equations. And then we'll be stuck on this. Maybe I'll put this in the notes tomorrow because I forgot to do that with the other hour. That's actually real simple. But this one, all right, what is this? An exponent or not? Is that an exponent or not? It actually is. When you get to the test generator, it stinks. This is the exponential chapter. So that's 2 raised to the 7 minus 3x. This is a non-graphing calculator question. You want to know why? I have 3 minutes to do this simple math. What's LO6? What's LO6? I don't care. What's x equal? You don't even have to know what logs are. What's x equal? Tell me. 7. Who sins? I'm not a sinner. There's no such thing in a public school. What's x equal? Did you do trig? Or did you just do matching? You just did matching. 7 to the x equals 7 to the 43rd. What's x equal? You just solved an exponential. No, you didn't. You just did matching. So what am I getting at? 4 can be rewritten as 2 to what power? What is 1/4? I said 4. I meant 1/4. What's 1/4? 2 to the negative second. Rewrite this as an equivalent scenario. And then what do? Match. You didn't drop the 2's. You didn't divide. You didn't do anything other than if 2 to this power equals 2 to that, the only way that can be true is if this equals that. So 3 to the negative x equals, what's 81 the same thing as? 3 to what power? Fumble. Wow, that was more than a fumble. I think we lost a student. Negative what? 4. That scared me. And by the way, solving this when you get x equals 3, I believe. Woo, man, that was a waker-upper.